Well, Andrew Beck is here to talk to us. I'll turn it off to. You can go ahead and share your screen, Andrew.
All right, thank you.
And he'll be speaking to us about lessons learned from high accuracy geospatial data collection and fusion in coastal communities. All yours, Andrew.
All right, thank you. Thank you again. Good afternoon. My name is Drew Beck. I'm a professional land surveyor with Continental Mapping, and I do appreciate the opportunity to participate in the WLIA annual conference. Today, I'll be discussing resiliency, lessons learned from high accuracy geospatial data collection and fusion in coastal communities. Like I was saying, last year, Continental completed a comprehensive survey, the mapping project in Texas, which I was the surveyor record, and which will be the subject of my presentation today. My goal was to provide you with some lessons learned, insights from the challenges we faced, and hopefully can benefit you on some of your future projects having some of the same tasks or requirements. My initial slides will give you an overview of coastal communities, and the slides following will be specific to the project we conducted in Port Arthur. Here. As we all know, coastal communities are crowded and millions of people live in these communities. And with that, encounter some risks and challenges, including high tides, flooding, sea level rise, hurricanes, and erosion, just to name a few. With that in mind, some of the goals of coastal communities include protecting its population, infrastructure, maintaining water quality, and supporting economic development. Today, we'll be talking about some of the challenges we encountered on our Port Arthur project, which is located in Southeast Texas, and as it relates to the hurricanes and recent flooding events. Let's see. Likewise, the coastal communities in Wisconsin along its Great Lakes share many of the same challenges as those communities populated along the ocean, such as water level rise, coastal erosion, maintaining water quality, and protecting the coastal population while encouraging economic development. Our area of interest today in our discussion, as mentioned, is the city of Port Arthur, and it also includes the Port of Port Arthur, both located in southeast corner of Texas, being separated from Louisiana by the Sabine River, as illustrated on the map. Port Arthur's population is approximately 55,000 and is located on the Gulf Intercoastal Waterway, and its main economic engine is driven mainly by the petroleum industry due to its proximity, and it has a long history of coastal challenges due to the flooding and hurricanes. As you can see on the map, shown by the red line, the city and the port, the nation's third largest waterway, are located about halfway up the Sabine-Neches Waterway. The Port of Port Arthur is located along the Gulf Intercoastal Waterway and serves as a massive economic engine to the region and the country at large. On the right, you see the coastal entry point for barges and the rail lines fanning out across the country along with barge accesses within the interior. The Port of Port Arthur serves as the main entry port in this area from which petroleum, steel, forestry products, and even military equipment are transported. Over the past 100 years or so, this region of the country has been no stranger to hardship, as seen in these photographs. Unfortunately, this area has seen an increase of hurricane activity and intensity, having an adverse effects on its coastal population. In the photos on the right, you can see the aftermath of Hurricane Harvey that made landfall in August 2017, which dumped some 45 inches of rain on the Port Arthur area. In this event, not only were some 20,000 homes flooded, but many lives were lost, and the impacts overwhelmed infrastructure, shut down refineries, and also had a huge impact on local economy with ripple effects throughout the U.S. As a side note, during the course of our project, our survey crews were directly impacted by Hurricane Hannah that made landfall in southeast Texas and southwest Louisiana in July of 2020. This event was nowhere near the scale of Harvey, but did directly contribute to power outages and local flooding. As one might imagine, our survey crews had booked hotel rooms well in advance of this hurricane, just to have them immediately canceled, and for a very good reason, to accommodate the first responders like FEMA, power crews deployed from other areas of Texas and from out of state. This in turn impacted travel time for our crews, both to and from the project, since the closest accommodations were located some 70 miles west in the outskirts of Houston. Ultimately, as a direct result of recurring weather events, it was apparent the port needed to upgrade the coastal protection system. So with some other stakeholders, the port engaged with the Galveston Corps to champion a project to improve the resiliency of the coastal infrastructure. The goal was to expedite the design and construction of levee improvements by mitigating flood risk and addressing risk associated with overtopping and relative sea level rise. Continental's task was to complete the surveying and mapping of approximately 8 linear miles of levees and/or flood walls, together with surveying the surrounding topo, which 5 miles ran through residential neighborhoods, and also survey a 23-acre parcel for proposed levee extension. And this was phase 1 of that project. That phase 1 included the following requirements: high accuracy mapping, location of above and below ground utilities, bathymetric surveys around pump stations, and including a portion of the Neches Riverway, together with a boundary survey of the proposed levee extension area. So with that background, let's talk about our project approach and how we address challenges, all in the hopes that they could be beneficial to you on future projects having some of the same tasks. In this illustration, you can see one of the aforementioned pump stations and on either side the limits of the hydro survey undertaken. Our first challenge, like many multifaceted projects, was the coordination of the stakeholders that included the Port of Port Arthur, both districts of Galveston and Tulsa of the U.S. Army Corps of Engineers, the Jefferson County Drainage District number 7, private landholders, including residents and corporations, and a full team of survey and mapping professionals. From past projects, we understood what really mattered was having iterative discussions on problem solving, including the use of the appropriate technologies that would provide the accuracy this project required, along with ongoing coordination and communication amongst all parties, defining roles and responsibilities of each organization. In a nutshell, understanding who was doing what, when, and where, and these regular discussions coupled with ongoing communications was ultimately our key to our success. Once we assembled the right project team, our second challenge was establishing a quality, high accuracy, horizontal and vertical control survey. On this project, excuse me, like this. On a project like this, and with many projects with involvement of multiple parties, it was absolutely essential to have solid foundation where all work performed and the collected data throughout the project area is tied to a high accuracy and centralized control network. This ensures data can be fused and merged together in order to derive whatever products required to assist in the future engineering design decisions. GPS was used to set up the control network, and this was our and the foundation or base initiated from primary and secondary control monuments that were local to the project. NGS data sheets provided the monument locations and other pertinent data which were supplied by the Galveston Corps. As many of you may be familiar, these data sheets can be found online on the NGS website for areas throughout the U.S. I would like to emphasize that for those of you who are thinking about your next project, to be sure to factor in the time and cost to effectively populate the network in and around the project area. And by all means, share that information with all parties. On the right, one of our surveyors is painting a photo horizontal and vertical control point. On the left, you can see the limits of our project. The lighter green represents the flight corridors we use for aerial imagery and LiDAR collection. The red triangles show supplementary survey control that was all tied back into the primary control monuments for collecting imagery and other surveying data collections tasks. Due to this project's comprehensive data requirements, the third challenge was to evaluate and select the proper technologies. And this dictated that we used multiple platforms and sensors. This exacerbated the coordination of parties. Ultimately, we decided on the following: fixed-wing manned aircraft platforms to collect LiDAR at 8 points per meter and imagery at 6 centimeters across the entire area of interest, except for the 23-acre levee extension area on the northern side of the project, which was collected at 3.5 centimeters. For the hydro survey, we used a remotely operated boat, supplemented with conventional surveying on areas of water around the pump station. Manned hydro boats were required along some of the open areas along the Sabine-Natchez Riverway. Boats were equipped with multi-beam and side scan sonar. This provided the bottom footprints and served to help identify pipes and other obstacles present underwater. For the subsurface utilities, we first called 811, the national call line before you dig, for a utility locate ticket to paint approximate locations of underground utilities within the public right-of-way. Crews then use geophysical methods for locating tonable utilities such as fiber optic cables, underground telephone, electric and gas, and really anything that could be potentially found with these geophysical methods. Our target tolerance was 6 inches plus or minus from center line of the utility, depending on the soil conditions. Finally, for the topographic above ground utilities and boundary survey, data was collected with total stations, GPS, terrestrial LiDAR that really came in handy around complete complex pipe racks and pump stations. For the fourth challenge, I would like to further discuss the project area and our aerial collection. On the left, you'll see flight lines and limits for collecting the LiDARs at 8 points per meter and imagery at 3.5 and 6 centimeters using manned fixed-wing aircraft. Those resolutions and point cloud destinies allowed us to use topographic and feature extraction to support our ground-based efforts, which really helped us in areas where rights of entries were limited or non-existent. With Continental having both land surveying and aerial capabilities at our disposal, we selected those densities to produce quality orthos and support photogrammetric efforts for validation of field work for producing comprehensive data sets. The fifth challenge was related to deploying the proper technologies to identify the buried utilities. There are 4 quality SUE or subsurface utility exploration levels, A, B, C, and D. Quality level A, which we did not use on this project, is locating the horizontal and vertical positions of utilities by digging test holes and potholes, thereby exposing utility. However, we did use the remaining 3 levels. Quality level B was the horizontal positioning of individual utilities, which we used our geophysical methods. Quality level C is the actual underground survey and mapping of the above ground utility features such as utility poles, manholes, catch basins with invert elevations, etc. And lastly, the quality level D, where utilities are derived from existing records, research, and sometimes verbal recollections to have identified individual utilities. In the 2 upper left photos, you'll see survey personnel using radiometric detection, looking or exploring for tonable ferrous utilities using the RD 8100 and Metrotech 810. And on the bottom below left, the one on the right, the detectable radar for locating storm surge and alignments, which also provides personnel the ability to track and identify other non-ferrous underground utilities. Ultimately, this underground information can be compiled and delivered in a 2D vector data set. The plan view image on the right was produced and utilized color codes to differentiate utilities such as electrical, gas, and wastewater, and communication lines. Our 6th challenge was selecting the right technology for the topographic mapping and collection of above ground utilities. For this, we deployed survey crews as shown on the left using traditional total stations, GPS, terrestrial scanners to collect data, and also used the imagery and LiDAR I referenced earlier given the complexity of the sites, and often due to the close proximity of utilities. Again, this information can be compiled and delivered in a 2D vector data set. Our 6th challenge was selecting the right technology for topographic mapping and collection of above ground utilities. For this, we deployed survey crews as shown on the left with traditional total station, GPS, and scanners to collect the data. Also using the LiDAR I referenced earlier, given the complexity of the site. This plan view of one of the pump houses in this next slide, you can see a storage tank and an example of some of the LiDAR data where berming around one of the storage tanks for protection can be seen, as well as other above ground features. The LiDAR in the next few slides shows the LiDAR that we used for picking up 20 points per meter to help validate utility locations. As a side note, prior to our crews entering the refineries and storage tank area, they were required to participate in safety classes and required PPE, including hard hats, safety goggles or glasses, ear protection, steel-toed boots, and fire retardant clothing such as snowbags. You will want to make sure to include these the next time you have projects in these heavy industrial areas. Like I was saying and mentioned it previously, we took the liberty to fly the LiDAR at additional resolution of 20 points per meter to help identify and supplement the underground new survey. I cannot overemphasize that using this technology is very beneficial in areas of access is limited or non-existent. Challenge 7 was the hydro aspect of the project. There were 3 substantial pump stations that were part of the overall levee infrastructure that offered their unique challenges. To understand what was going on underwater and surface, we required to map underwater feature and the bottom footprint of the water bodies. To achieve this, we employed a remote operated Teledyne Z boat, as shown on the left, equipped with multi-beam echo sounder and a couple of R10s for positioning the pilot, positioning the locations. The pilot remotely operating the Z boat is seen in the top middle photo. In the middle photo, you can also see the water around the pump house. And lastly, when the water was too shallow for the Z boat, surveyors went out and waders to collect data conventionally. On the far right, you can see the results that were ultimately fused with the surrounding topographic survey, creating a data set that engineers could use for design purposes. Challenge number 8 also posed a secondary hydro survey component. In the top middle photo, the AOI is circled in red along with the Sabine-Natchez Riverway in order to support the next phase of design and construction of the Corps' project. Corps requested this hydrographic survey to research and search for anchors, moorings, chains, and buoys, etc., within the riverbed, and also the validation of its footprint. On the left is a manned boat equipped with bottom and side scan sonar, as well as a magnetometer for locating ferrous materials. On the illustration to the right, you can see where dredging activities had occurred and where scarring of the riverbed happened from dragging of anchors and other ferrous dragging of anchors. And the other ferrous materials the magmameter picked up. The white areas in the illustration represents where ships had been moored. So subsequently, data collection was limited in those areas. All this data was gathered and merged into together and delivered. The 9th and final challenge was undertaking the boundary survey. Technologies employed for this were GPS, total stations, terrestrial scanners, all in support of the proposed levee extension, as shown in the red circled area above. The bottom left photo shows some of the parcels that were surveyed. And the following 3 drawings were also part of the land survey we conducted. These parcels consisted of both residential and heavy industrial refinery properties. The real challenge here, as with most land surveys, was the right of entry. The real estate department of the Galveston Corps and the Jefferson County Drainage District was instrumental in securing rights of way to most of the parcels. However, there were a few parcels where owners were unresponsive to the request, so we were unable to survey every parcel we would like to. However, our aerial survey did contain surface content we're able to leverage to deliver along with the completed boundary survey on the right. In closing, I have a few recommendations. Ensure that you have a high quality ground control survey, which is extremely important to deliver products properly fused. Communications amongst stakeholders is paramount, and build a cohesive team and identify roles and responsibilities. Also, for the use of proper technologies, it is vital that you have a cohesive team. Also, be sure to secure rights of way early on the project life cycle for utility location and boundary surveys, and confirm the statement of work specification and project deliverables. On this slide, I've included my email and also Paul Braun's email if you have any questions. But right now, I probably have a few minutes and I'd be glad to answer some of your questions. And I have one of our GIS experts on also to answer any GIS questions you may have. So with that, I'll be glad to open it up.
Thank you so much, Andrew.
Okay, thank you very much.